Okay, before we finish the lecture one slides, we need to talk about limits of sequences of sets, which is going to tie into how we think of continuity for our probability function. So let's define what we mean by the limit of a sequence of sets. So you might remember that for a sequence of real numbers, for the limit to exist, you need something called the lim sup and the lim inf to be the same and to be equal. It's the same with sets. So let's talk about a sequence of sets indexed by n, and we want to ask like, what do we mean when we take the limit of the sequence of sets as n goes to infinity? We say that it exists and it's equal to a set A if something called the lim sup of the sequence of sets and the lim inf of the sequence of sets both exist and are equal to the same thing, to that set A. And these, the lim sup and the lim inf, have special definitions for sets. Lim sup is this intersection beginning from n equals 1 up to infinity of unions beginning from n up to infinity, so indexed by k. Lim inf just flips the those signs upside down. Okay, so for lim inf we've got union of intersections. For lim sup we've got intersection of unions. Let's try to work out what is meant by these kind of crazy looking things. This one, we say that if an outcome in the sample space belongs to the lim sup set, that means it occurs infinitely often in the sequence. That means infinitely many of the sets in the sequence contain that outcome. Okay, so the lim sup is the set of outcomes which occur infinitely often in the sequence. Lim inf has a different interpretation. We call it eventually, and we're going to make sense of both of these. But the lim inf set of a sequence of sets is the set of outcomes which eventually occur. Okay, we're going to break down what those mean. So let's start with number one. So I want to make sense of this lim sup business. So lim sup as n goes to infinity of a sequence of sets A, we've defined it as this intersection of unions. So the intersection begins at 1 and goes up to infinity, and the union begins at n and goes up to infinity. So we use a different index, k. Okay, so now it matches this. All right, how do we put into words all of this? For our intersection, the key word is going to be for all, or for every. So intersection means every single one. So we're going to say this means for all n greater than or equal to 1. So this for all symbol is coming from the intersection. And then union, as we discussed before, means it means at least one, or there exists an index here. So so maybe let's write it as this is the set of omega, set of outcomes omega, such that for all n greater than 1, that's how we interpret this intersection, there exists k greater than or equal to n, such that omega is in ak. Okay, so there exists goes along with the union, and the for all goes along with the intersection. Okay, so let's think about what this whole phrase means then. It means for every n, I can always find some set later in the sequence which contains my omega. So this whole set is the set of omega such that for every n greater than 1, I can always find a set later in the sequence which contains omega. So if we think about what this means, if I start writing out my sequence, um, it means I can always like begin at some point in the sequence, and after that I can always find another AK which contains omega, no matter where I begin in the sequence. So I could begin way out here, and I would always find another set beyond that which contains omega. So this is omega, such that omega is in the sequence infinitely often. Infinitely often. So for an outcome to belong in this set, I have to find it in an infinite number of these sets in the sequence. So that's how we get this I-O, or this interpretation of infinitely often from the lim sup definition. Okay, and so we abbreviate that as I-O. Let's think about the lim inf. So lim inf, n goes to infinity, of the sequence an. This is union n equals 1 up to infinity of intersection k from n to infinity. Okay, let me write it down clearly. Okay, so how can we interpret this? Union means there exists, well, we'll start by writing it as, so this is all outcomes omega such that there exists an n greater than 1 such that, and now we consider how we interpret this intersection, such that omega is in AK for all k greater than or equal to n. Okay, that means if I think about writing out my sequence, at some point there's an n. At some point I get to an, and then after that, omega is in every single set after that in the sequence. That's how we can interpret this. There exists some n such that after we reach that set in the sequence, the outcome is in every single one. And so we use the word eventually. So this is omega such that omega is in the sequence eventually. That's the word we've decided to use, and sometimes that's abbreviated EV. Okay, let's practice just finding the limit of a sequence of sets now. So let's say I've got an is this for all n greater than 1. So we want to check if the limit exists, and then if so, give it. To check if it exists, what I need to do is find the lim sup and the lim inf, and if they're the same, then that set is the limit. So let's start by writing lim sup as n goes to infinity. That's the one that's intersection and then union, AK. So how can we do this? Let's just take one piece at a time. So this is intersection n up to infinity, and then the union, maybe it helps if I just start writing it out. 1 minus 1 over n, union, let's see, it's going to be then 1 plus n, 1 minus 1 over n plus 1, union, and so on. Because look at my k is beginning at n and then going up to infinity. So I'm going to get this when I expand this union. All right. If I think about this union, I'm getting intervals which are wider and wider as I go this way. And and well, what you can think about is this is going to be just the interval 0 to 1. Okay. Once I take the union of all of these sets. Okay, so you might need to do some extra work to convince yourself of that. You could show, you could do over on the side, you could try to show mutual containment of this. But I'm not gonna show it in detail. I think it's reasonable to believe that this, if I take their unions, is going to give me the set 0 to 1, not including the endpoints, because I'm never going to get all the way to 0 and all the way to 1. And now if I take this intersection, I'm just left with 0 to 1. Okay, so let's take the lim inf of this. And so this one, I've got to begin with the union and then intersection n up to infinity ak. Okay, so now this is going to be the intersection. Okay, 1 minus 1 over n intersect 1 over n plus 1 up to 1 minus 1 over n plus 1. The intersections keep going. And now, if I take the intersection of these, I'm going to be left with just this first set, because this is the narrowest interval, and it's contained in all the other ones. So I'm going to wind up getting this, n equals 1 up to infinity, and this now is just what I had here, and so that's the interval 0 to 1. All right. So since the lim sup and the lim inf are equal to each other, I can say that the limit of the sequence of sets an is 0 to 1. All right. Now, another concept we need to touch on before we leave these Lecture 1 slides behind is the concept of increasing and decreasing sequences of sets. We call a sequence of sets increasing if each one is contained in the next one. So a picture of that might look like this. Here you've got A1, then you've got A2, which contains A1, then you've got A3, and then you've got A4, and then A5. So each set contains the previous one. Okay, so this is increasing. And then here's a typo, that should be 2. Decreasing is just the opposite. So it means all the subsequent ones are contained in the first one. So A2 is contained in A1, A3 is contained in A2, and so on. Let's show one thing related to limits, just as an exercise. If I have an increasing sequence of sets, which looks like this picture, then if I take the limit of that sequence, I'm going to wind up with the union of them all. That kind of makes sense, because it's like I should get out to kind of the biggest one. But let's go ahead and prove that using our definition of lim sup and lim inf. Okay, so let's check on lim sup first. This is, remember, intersection union, so n going from 1 up to infinity, k going from n up to infinity of ak. All right. Now, I think the easiest way to proceed is by writing this union out as a set of outcomes. It's a set of outcomes in the sample space such that there exists some k greater than or equal to n such that omega is in AK. This means this is a set of outcomes where um, it's in at least one of these sets AK, where k is greater than or equal to n. Okay. Now, how can I sort of go further with this? Because I want to show that this lim sup is the union of all these a's. If I look at this intersection and then look at this here and think about it, I'm saying intersection means this holds for n equals 1, and it holds for n equals 2, and it holds for n equals 3, and it holds for n equals 4. It holds for all n. So I can use that intersection to say this is the set of outcomes such that there exists k greater than or equal to 1, such that omega is in AK. Because if this holds for every single n, then I can just say it holds for, like if it holds for n equals 1, then it also holds for n equals 2 and n equals 3 and so on. So I can use this intersection to change this n to a 1. And from what I know about the definition of union, this is just, it's nothing but the union of all of these AKs. So this is just the set of outcomes such that the outcome is in at least one of these. And the way we say that is there exists some k such that omega is in AK. All right, so we've shown that the lim sup is indeed this union. Let's look at the lim inf. I guess I can move this down here because I'm going to keep going on this page. Lim inf of an. So this one is union first, then intersection. K equals n up to infinity AK. All right. So if I think about this intersection, let me just write it out. This is going to be an union an plus, sorry, not union, an intersect an plus 1, intersect an plus 2, and so on. Let's think about this. I have an increasing sequence of sets, which means a1 is contained in an plus 1. So I have containment like this, I have containment like this, containment like this, all the way along. So if I take their intersection, I'm just going to get the smallest one back. It's like if I have A contained in B, then A intersect B is just A. And so I get from that whole, from all these intersections, I get just an out. Okay, so that's the same thing as that. So I can say limit of an is equal to union of an's for an increasing sequence of sets. Okay, similarly, you can show that for a decreasing sequence of sets, if I have A1, which contains A2, which contains A3, and so on, you can show that this limit is the intersection of all of those. This will be on your homework number 2. I think I put it on your homework number 2. Okay, and you can use similar arguments. Okay, so one last thing I want to talk about is um, the probability function and how these sequences of sets are related to the probability function. So the probability function we can say that it's continuous um, in the sense in this sense. So if I begin with a probability space, that means I've got a sample space, a sigma algebra on the sample space, and some function that I put sets into it, and it gives me probabilities out. If I have a sequence of sets with a limit, then what we find is true of our probability function. So probability function means satisfies the Kolmogorov axioms. What we find is true of the probability function is that the limit of the probability of the set an is equal to the probability of a. That means I can pass the limit through the probability function. So if you imagine a function that that goes from like the real numbers to the real numbers, and you have some sequence of real numbers like this, we say f is continuous if the limit of f a n as n goes to infinity is f evaluated at the limit. Okay, so recall from your studies of calculus or analysis or something. So we have the same kind of idea with the probability function, but instead of sequences of real numbers, we have a sequence of sets. Okay, so we have this property of continuity, which means I can pass this limit inside the probability function. Okay, it's hard to prove this. For us, we're just going to prove a special case. We're going to prove that if I have an increasing sequence, and we just showed on the previous slide that for an increasing sequence, the limit is the union of all of them. In this special case, we're going to show that the limit of these probabilities is the probability of the limit. Okay, so we want to show for an increasing sequence that limit as n goes to infinity, probability an is equal to probability limit as n goes to infinity an. So that's the continuity property. Okay, so let's do it. Okay, so here's the proof, and we're going to use some fun things that we know how to do. So firstly, we know that the limit, this limit here, which I'm writing as just a up here in the statement of the result, is the union of these because the sequence is increasing. Remember, this is what we just showed. So we just showed back here. It's this result. For an increasing sequence of sets, the limit is the union. Okay, so I just want to show limit of probabilities is the probability of the limit. And I'm first just observing the fact that the limit is the union. So now what I want to write down is, so I want to kind of play with this infinite union. And what we've learned is like to deal with an infinite union. I'll just say with a union. to deal with a union, we want to like change it to a union of pairwise disjoint sets, because this just seems to help us in many situations. When I've got a union of sets and I want to take its probability, a first step that we often find useful is to rewrite the union as the union of pairwise disjoint sets, because then I can write the probability of this union as a sum because of the axiom of countable additivity. So let's think about how I could write this union as in another way, as the union of pairwise disjoint sets. So I have that it's an increasing sequence of sets, which means that each one fits inside the next one. And I know that the union, I get like the limit of all of them, or the limit is the union of all of them. So if I want to, say, take the union of these guys, what I might think about doing is defining what we sometimes call ring sets, or a fancier word is annulus sets, if you want to be nerdy. And we'll call them, we'll define the first one, R1, to just be A1, so this one. And then R2 is going to be A2, but only the part which is not A1. So R2 is going to be just this ring or annulus, and then R3 is going to be the new contribution of A3, so the part of A3 which is not in A2, and so just this one like that, and we keep going. So A4 is going to be just this one, R4 is going to be just that one, and so on. So let's say Rn is like An, but take away An minus 1. So R1 is defined this way, and then we define the rest of them this way. Now, if I take the union of my Ans, it's equal to the union of these Rn's. But these have the advantage of being pairwise disjoint. So, what can we say? The probability of this union is the probability of my union of pairwise disjoint sets. But since these are pairwise disjoint, I am happy because I can now write this probability of a union as the sum of probabilities. And this is the axiom of countable additivity. Countable additivity. That's axiom number 3. All right, so now I can think about this sum of the Rn's. So this is going to be like probability of R1 plus probability of R2, and so on. But let me, for a reason that will become clear in a moment, just take the first one out, probability of Rn, like this. Let's think about these probabilities over on the side. So probability of R1 is the same as A1, so it's just going to be probability of A1. But then for these other Rn's where I'm defining it by taking away the previous An, I've got for n greater than or equal to 2, probability of Rn is probability of An take away An minus 1. And so this is An intersect An minus 1 complement. And a little while back we studied a rule about this. This is probability of an minus probability of an intersect an minus minus this. Okay, and so if we can scroll up and find this, where can we find it? Way back right here. So we showed that. Okay, so I'm just using that one. But since an minus 1 is contained in an, this intersection probability is just the probability of an minus 1. Okay, so this is like going on in our head. All right, so now I want to come back. Let's see, let me make this all some different color. So that's kind of work we did over on the side. So how can I represent this now? This is just probability of A1, and this is n equals 2. This is probability of an minus probability of an minus 1. Because of all this work that we did here. So all of that work. Now, let's not lose sight of what we were trying to do. I want to show somehow that this is equal to the limit of probability of an as n goes to infinity. Remember, that's what I want to show. I want to show that this is equal to this, because in here this is limit an as n goes to infinity. So how can I make this, how can I get the rest of the way here? Let's think about it. Here I've got an infinite sum. An infinite sum is nothing but the following. This is like limit as n goes to infinity of, let's say, I equals 1 to n pai minus pai minus 1. So whenever you have an infinite sum like this, it's just the limit of a finite sum where this one goes up to infinity. Okay. So having written it that way, I can pull the limit all the way outside and put PA1 plus sum of I equals 1 to n, PAI minus P of AI minus 1. And if I study the inside of this, this is going to look like, oh, sorry. I'm starting at I equals 2, because here I started at n equals 2. Okay, I equals 2. Easy to mess up your indices. Okay, so I remember because the A1 is here, so this sum is beginning at n equals 2. So this infinite sum is just the limit of this sum as n goes to infinity. Okay, and this is going to be like probability of A2 minus probability of A1 plus probability of A3 minus probability of A2, and so on down to probability of an minus probability of an minus 1. So this whole thing is really just probability of an. And so I've got what I wanted. So I have now probability of the limit of the ANs, which is this union, is the limit of the probabilities of the ANs. So I am done with the proof. So we've shown that if I've got an increasing sequence, then I have this nice continuity result for my probability function. You can show that it's in general continuous, but you have to use some harder arguments. So we're happy with just being able to show number one. You can use, well, I think maybe it also gets a little tricky when you try to show number two, but we're satisfied in this class if we can show number one. Okay, so we're done with our lecture one slides.